Welcome to section 2.5. This is about LU factorization. And this is the first time we've seen a matrix factorization. I'll have to tell you I have some mixed feelings about this section. Factoring matrices is a super important idea. This particular factorization, mostly useful for people writing programs. So unless you are coding, you're probably not going to end up using LU factorization a whole lot. However, it's a great way to get introduced to the idea of factoring matrices. So keep that in mind as we go forward. I also think LU is kind of cool because it's a relatively new mathematical technique. Most of the things you learn in math are like thousands of years old, or at least hundreds. This idea is less than 100 years old, and it's due to somebody whose name I cannot pronounce, either his first name or his last name, but it is this guy right here. Super smart dude. And right here in his Wikipedia article, almost the last line, the LU decomposition was introduced by him in 1938. So it's not even 100 years old yet. Okay, so let's talk about what this actually means. But before we dive too deep into that, I want to remind you of a couple things. So the first thing I want to remind you of is really basic, just what it means to factor. And we're not talking, if you're thinking like quadratic formula, we're not talking algebraic factoring with variables. We are just talking factoring numbers. Numbers in a matrix for us. But let me just remind you that when we say factor a number, we literally mean just break it down into multiplication. So there's a factoring of 6, not the only factoring, of course. So that's one thing I'd like you to remember, is just that's what factoring means. We're going to do the same thing with a matrix. We're going to break it down into two other matrices multiplied. I'd also like you to recall that solving triangular systems is easy. Easier anyway. So if you have a augmented matrix that's not triangular, then you have to do full row reduction, and you can do it, but it is some work. If you have, however, a triangular, and keep in mind triangular means that there's zeros below the main diagonal, or possibly all zeros above the main diagonal, one way or the other. This one I'm going to put zeros below the main diagonal. Now it's pretty easy, right? Because you can essentially do back substitution. You can say this bottom row here means 3x3 equals 3, so it's very easy to get x3 as 1. And once you know that x3 is 1, you can go to the next row, which says 4x2 plus 9x3, so just plus 9, equals 2. Oops, that's x squared, not x2, not x squared. Subtract the 9, so you get 4x2 is negative 7, and x2 is negative 7 fourths. And I didn't make this example up very well because now I have an ugly fraction, but you could go back to the top row and substitute x3 and x2 and get x1 very easily. So triangular, easy to do by hand. I basically did it right here. Non-triangular, you have to do, full row reduction probably. Okay, so the reason I mentioned that is that LU factorization is a factoring into triangular matrices. So let's take a look at an actual example. And I want to give you, first of all, one that is factored already. So here is some sort of matrix, full non-triangular matrix A, and it's been factored into, they call this one L because it's lower diagonal, right? All the entries, all the non-zero entries are below the diagonal, 1's on the diagonal, 0's above the diagonal. And the U, of course, is an upper diagonal matrix. All the non-zero entries are above the diagonal. The L always has 1's on the diagonal. The U doesn't necessarily. And the first thing I'd like to check is just to make sure that we actually have a proper factorization here. In other words, let's just check that when you multiply L times U, you actually get A. And I'm going to try to actually do this by hand, because I think it's helpful to see the inner workings here. So I'm going to use the sort of repeated vector multiplication here. So first of all, I'm going to multiply 3, 0, 0 by L. And then I'll try to do the same thing with 4, 2, and then last one. Okay, so 3, 0, 0 times L means 3 times the first column, 0 the second column, 0 the third column. So basically it's just 3 of the first column, which you can see is going to make the right first column. 3 times 1, 2, negative 1 is 3, 6, negative 3. So yeah, we definitely got the first column going. That's great. Multiplying the second column by L, should say 4 of the first column plus 2 of the second column. So let's see if we can do that. 4 of the first column, 2 of the second column. So that'd be 4. 4 times 2 is 8. 2 times 1 is 2. So that makes 10. And let's see, where am I? Oh yeah, 4. So negative 4. And 2 times 3 is 6. That's positive 2. Okay, so far so good. It looks like it's working. For this final column here, I need negative 2 of column 1, 1 of column 2, and 3 of column 3. So okay, let's work that out. So negative 2, 0, 0, so negative 2 there. Negative 4 and 1 is negative 3. And let's see, that'd be 2. Plus 3 is 5, plus 3 is 8. Okay, hey, look, it checks out. We got A back again. Okay, so fine. You're like, great. I could see that someone factored this into LU. Now, how do we factor into LU if we were just given A? Of course, that's one of the main tasks for the homework tonight. Before we get into how to actually factor, let's look at using the factorization a little bit. So let's say we had some matrix equation we were trying to solve with this A, same A here. So let's say it was A times X equals, I'm just making this up, equals 1, 2, 3, right? So we're trying to solve. And we could do that with A either with full row reduction on the augmented matrix, or now that we know about inverse matrices, we could find A inverse and multiply it by B. But let's look at what this would look like if we replaced A with LU. Okay. So let me point out that U, if I multiplied U by X, and X is our unknowns, but more importantly, X is a single column, it's a vector. So you multiply U times a vector, you'll get a new vector, right? And I am going to just call that, for sake of convenience, I'm going to call it Y. But notice what I am trying to solve right now is a diagonal triangular matrix times unknowns equals b. So like we just said on the previous screen, that's triangular. So it's easy. So pretty easy to solve for y. And once we know what y is equal to, we can say, okay, I've got y, but keep in mind that y was just a nickname for u times x. So once I've solved y, I can solve ux equals y, and this u is also triangular, so this is also easy. So easy to solve for x. So that's just a little bit of the theory. In the next video, we're going to look at an actual example of how to do this. So I will see you there.